Welcome to solverfy.
Problem 8.101. We have a ballistics testing setup. We're going to be shooting bullets at a block of wood that's sliding on a table with some coefficient of friction. In fact, 0.38. And we've got a that's going to be compressing. And given this table of bullet masses and their muzzle velocities, we want to figure out, first of all, which one would we want to have the maximum change in the maximum compression of the spring. Then we want to say if we want that maximum compression to be 25 centimeters, what should the spring constant be? And then for the bullet which produces the least deflection of the spring, what will that deflection be? So, well, actually, this is sort of independent of any part. So when the bullet hits the block here, a conservation of momentum says that the mass of the bullet times the speed of the bullet is going to equal the mass of the block plus the mass of the bullet times their combined speed, or the speed of the combined object. For brevity, let's call this capital M. And so we see that the speed that the block with the bullet stuck in it is going to start moving at is going to be the ratio of the bullet's mass to the combined mass times the speed of the bullet. So that's good. Now, the block with the bullet in it is going to start moving with some kinetic energy. As it moves a distance d, let's call it, it will both compress the spring, causing potential energy to be stored in the spring, and also lose energy due to the force of friction doing work on it. So the force of friction, which is going to be doing negative work, is going to be the coefficient of friction times the normal force, which is the combined mass times gravity. And this will be then multiplied by the distance it travels, because work is force times distance. And so the initial mechanical energy we start with minus what we lose to friction is going to go into compressing the spring. So this is the potential energy stored in the spring. And so for part A now, we can see that if the greatest speed of the combined object will maximize d, because if we move this over here, we've got some quadratic in d is equal to some constant, and so the bigger this is monotonic. As d increases, the value of this as d increases, the value of this increases. So maximizing this speed v is going to maximize the compression, and that's going to happen when the momentum of the bullet is maximum because this doesn't really vary a whole lot. We're told that a grain is equal to 64.8 milligrams, and then this is 2 kilograms, so that's not going to change a whole lot compared to the initial momentum of the bullets. And so for this first part, we just need to know which one has the highest momentum. And for that, we don't need to worry about converting this into SI units. We can just use units of grain feet per second. And doing that, we find that bullet C, and you just write these out in a little table on some paper or something. C gives you the maximum compression, and B gives you the minimum compression. Now for part B, we want K such that bullet C produces a compression of 25 centimeters. So, going back to our equations we had, we know that the combined speed of the block and bullet is equal to the speed of the bullet before it hits the block times the ratio of the mass of the bullet to the combined mass of bullet and block. And we know from our energy equation that speed squared times the combined mass, etc., 1/2 minus mu mg d is equal to 1/2 k d squared. So now if we convert the mass of the bullet and the speed of this bullet to SI units, so we were told there's 64.8 milligrams per grain, and so this is 15.6 milligrams. Oh, no, I'm sorry. I forgot there are 1 million milligrams in a kilogram. Well, let's just put it in scientific notation in kilograms. Scientific notation. Sorry about that. Times 10 to the negative 2 kilograms. And so the inch is conveniently has a defined value in centimeters. And then 12 inches equals 1 foot. So you can do the unit conversions to find that its speed is 259 meters per second. 59 meters per second. So having done that, we can find that V is going to be 2 meters per second. Now K, we just multiply both sides of this by 2 and divide by d squared. And so we have, this is m d squared minus 2 mu m g d divided by d squared. Recall this is our 25 centimeters. We know the rest of these things now. And so then this gives us a spring constant of 69 newtons per meter. So for part C, we want to know what D is for the bullet B, which produces the least deflection. So returning to our equation back here, we see that we'll have kd squared plus 2 mu m g d minus mv squared equals 0. And we're going to use the quadratic formula to find out what d is. It's a little bit tedious, but right. So we know that it's negative b, so minus 2 mu mg, so k is a, 2 mu mg is b, and negative mv squared is c. We're going to want the positive root, because otherwise these will end up being negative, because you'll have a negative number minus another negative number, and that's no good. You don't want the sort of non-physical situation where the spring actually stretches out to the left when the bullet had been going to the right. That would be the sort of thing that would keep you up at night. So 2 mu mg squared, here's our b squared, minus 4 ac. So that's k mv squared divided by 2a. A is k. Easy enough. And then we just plug all of these things in. We know that the mass of bullet B is 8.1 times 10 to the negative third kilograms, and its speed is 288 meters per second. 8. Using the sort of quick facts about inch to meter conversions we have here, and foots or feet. It's 12 inches. 1 inch is by definition 2.54 centimeters. I guess that the United States decided to let the International Bureau of Weights and Measures worry about how long a centimeter is, and then with whatever they decided on to define the inch. Anyway, digression aside, plugging all those things in, we know what mu was. K we just found in the previous part. We're going to find a d of 12 centimeters. And so this is nice. We have, if you recall, d max was 25. Okay, it's either 25 or 12 centimeters or 0.12 meters. Pardon me. So the maximum displacement of the block is going to be 25 centimeters. The minimum one from the bullets in the table is going to be 12 centimeters. So not only is this is not too small to measure by any stretch of the imagination. It's you quite easily. This is this is over 4 inches, almost 5 inches. So this is something in the neighborhood of 10 inches. So this is actually within the range of bullets that we're looking at least. This both provides like a 2-to-1 ratio between the displacements of the minimum and maximum bullets, and also so there's probably a fair degree of separation, and so you can resolve them easily. And then also neither of these are, well, obviously the 25 centimeters isn't difficult to measure, but then this also works out to be pretty easy to measure, and so you don't have the bullet hit and it barely moves or something. So this turns out to be a reasonably practical setup for the purpose at hand. And so yeah, if you ever need to make a setup for identifying bullets, this is how you might go about it.